Okay, thank you very much. So I'm really happy to be here, and this is my second time, no, more than second time at IPAM, because I used to be a PhD student not far from here in Pasadena around 7 years ago, and I would come here a lot. And I remember sitting in this room and listening to Yanis and Art Voter and other people give talks here, so it's very exciting to be back in the same room again. And I'm a relatively new professor at University of Maryland. I started 2 years ago, so I just started my third year. I'm jointly hosted in the Department of Chemistry and Biochemistry and a nice little institute called IPST, or Institute for Physical Science and Technology. And essentially, I'm interested in performing molecular dynamic simulations, which can go to really long timescales and look at problems from biology. This is how a ligand unbinds from a protein. Problems in drug design, we are starting to get interested in RNA therapeutics. And also problems in material science, such as how does a crystal or a liquid droplet nucleate. And for this, we use a variety of neural network architectures. The deep learning in our work, as I will try to show you, comes in quite naturally in a way. It's not that one fine day I woke up and decided deep learning is getting hot and I should use it. It didn't happen that way. It came in a very nice manner. And we are also very interested in understanding the links between deep learning and statistical physics. So when I gave this title, I thought I will talk about the autoencoder stuff and also about the LSTM stuff, or GRUs, and also a bit of reservoir computing, but I'm going to totally skip this stuff because my student is still working on it, and we have some good results, but they are in stealth mode. So, and this is my group at Maryland. We have 4 PhD students coming from different departments, and all of them are good coders, which is quite essential for work like this, but they also need to have a strong background in physics, chemistry, and biology. So they don't need to know that many things, just 4 things. And we are funded by a variety of sources, such as Schrödinger, some seed funding from National Cancer Institute, Petroleum Research Fund, and we use supercomputer time wherever we can get hold of it. And so I'm going to start by highlighting something, that deep learning and statistical physics in a way have same demons, which go by different names, or sometimes even the same names. Here there is a screenshot from a chapter from a book, which is called Confronting the Partition Function. See, it talks about partition function. It also talks about annealed importance sampling. It talks about Chris Jarzynski, who used to be my head of the department at Maryland until a few months ago. A chapter such as this could be very well coming from the book on deep learning, or a book on statistical mechanics. In this case, this is the Goodfellow book, and this is Mark Tuckerman's book.
Which one is it?
It's the top one. If you read, you can get a hint, right? Tuckerman won't talk about unidirected graphical models, maybe in a few years, but so you can see. But if you just look overall, see, even Yanis got confused for a bit. So, and this has been, we have been thinking about things like this, KL divergence between 2 probability distributions. When it's large, how do we sample? This has been there in statistical physics for a very long time. And that's kind of a common link which we are trying to explore. And simulation-wise, we do something very, very simple, which is to solve Newton's law of motion. If you had 2 atoms, you could do it with pen and paper. If you have 3 or 100,000 in our case, typically, you have to use supercomputers. But we would like to do very ambitious things with Newton's law of motion, which is to look at drugs such as this. So this over here is a drug called Gleevec. It is used to treat certain forms of cancer, especially chronic myeloid leukemia. When it came out in 2001, it was a blockbuster drug. People whose mortality rate was something like 90% dropped down to 20 or 30%. It was a superstar drug. I used to think it's the only drug that had made it to the cover of Time magazine. Recently, it was pointed out to me that Viagra also has that same honor. So it's the second drug to make it to cover of Time magazine. But a few years later, the same drug, in the context of other drugs, made it to the cover of Newsweek with the title Getting Cancer Wrong. So what it does here is to go and block something called a protein kinase. Essentially, protein kinase transfers phosphate from ATP to ADP. So it's like a credit card. If it falls in the wrong hands, you can have lots of energy transfer leading to tumor growth and problems like that. So what happens in the body is when this drug goes and binds to a protein, a few years later, or at any point, the protein starts to mutate. And some of these mutations, and these mutations make the drug ineffective. Some of the mutations, you could imagine why they would have a role to play. They are quite close to how the drug binds. But some of the mutations are so far out, if you just looked at the crystal structure, you would not be able to tell that this mutation, for instance, or this mutation would have impact on what goes on over here. It's almost like spooky action at a distance in quantum mechanics. So we would like to use MD simulations to understand things such as this, to really go beyond the crystal structure and see what's going on at per residue by residue basis or per atom by atom basis. But of course, these things are really slow. A drug does not dissociate from a protein in a microsecond. Most drugs of practical interest, they dissociate on timescales of milliseconds, minutes, or even days. So molecular dynamics has a huge timescale problem, and we saw something like this in Stefan's talk also in the last one. So it's a differential equation, right? So you integrate it with a time step of femtosecond. With supercomputers, you can get up to maybe, well, even on standard NSF supercomputers, it's easy to get up to 50 nanoseconds in a day. So if you run it for 20 days, you're up to 1 microsecond, which is quite impressive. And then, of course, people realized that hardware which was being developed for keeping undergrads from getting bored could be put to better use. So GPUs came in the picture, and I think they also accelerated the process a little bit. And then a very rich person got involved in the problem, right? David Shaw. So this was when I was sitting in IPAM 10 years ago listening to Yannis give a talk. And they published a paper where for the first time they could fold a protein and unfold a protein in unbiased MD. So we had a discussion about long timescale evolution of molecular dynamics methods, and they showed for the first time that they actually ran it for a millisecond, and it stayed the way it was supposed to stay. Nothing broke apart. And I think it made it to the cover of Science magazine back then. So 10 years later, have we really pushed this way more? To some extent, yes. On this special computer that David Shaw designed on Anton, now I'm told people can reach up to 20 microseconds in a day, which is really impressive. That's super fast. So they are really pushing the limit, but still there are many things such as nucleation of a crystal or the dissociation of a drug that are much slower. And I believe there will always be sampling challenges because this is just with classical force field. A few years later, maybe we would like to do polarizable force fields, where the problem currently is that you can reach maybe something like 20 nanoseconds in 2 weeks. They are so slow. Okay, and then we will have a specialized computer that solves that. What next? Well, we would like to do Born-Oppenheimer molecular dynamics. We will treat the nuclei also, and electrons also correctly. Maybe we will have a computer for that. What next? One day we would like to do fully quantum dynamics, and it will keep pushing. So there will be always need for enhanced sampling methods. And the reason why just brute force computing, parallel computing has not made so much of an impact in this time scale problem as compared to length scales is essentially the time is sequential, right? I cannot have a group of 100 graduate students and just divide. You look at T1, you look at T2, you look at T3, it's not going to work. Some methods try to do that. Markov state models, parallel replica dynamics, that's the hope. But
There are these what is it that you want they call it paranormal, para something, parallel integrators?
yeah, people have tried, but they have issues. So, I mean, yeah, but that's the question we would like to address is how much of the, past do we really need to know in order to predict the future, the keyword being reliably. And that brings us to a very common concept in physical chemistry, which is a reaction coordinate. Now, reaction coordinate can be defined in many, many ways. I have been to workshops where for 7 days people argue over how to define it. A poor man's working definition of it, and we will quantify it later, is that the true system is very high dimensional. It's made of lots of local minima and transition states and everything. A reaction coordinate is a projection on which, so essentially, you can always define a free energy from the high dimensional potential energy, right? This is just a definition. You have integrated out every other degree of freedom, except the ones you want to keep. And you can always come up with a free energy that looks like this, but this free energy might be meaningless. It won't capture any mechanistic information. The saddle points could be deceptive. Even the local minima could be deceptive. So reaction coordinate is one such projection in which the free energy is actually meaningful. It carries mechanistic information, and other degrees of freedom that you have not captured in the reaction coordinate are either white noise or colored noise with a very short memory kernel. And we will quantify this in a moment. But I want to show you what we can do if we have such a reaction coordinate. We can play a lot of tricks. One of the tricks we can play, so normally molecular dynamics, if you look at the free energy projected as a function of some reaction coordinate, would be trapped in one basin. An event that takes it to the other side would be a rare event. Now you could do something called metadynamics, which has existed in one form or the other over many years, where you start building bias into the dynamics of the system. So it's like you're stuck in a well. Wherever you get stuck, you add a little bit of sand. At some point, you will fill up the wells, go to the other well, fill up more sand, escape from that well, and in the end, you will have a diffusive dynamics going on. If you look at the amount of sand that you have added, you can recover the underlying free energy surface. When I was a postdoc with Michele Parinello, we wrote a paper where we showed for good reaction coordinates how to even reconstruct the dynamics out of such a process. I'm not going to go into this, but I will be using this. So, this is a typical enhanced sampling method. That's a whole cottage industry in molecular dynamics, and there are many, many such methods, and they are all traditionally a three-step process. You pick a coordinate, you perform your free energy calculation, and if you're still feeling brave enough, you go and think about the kinetics. It's very linear, mostly. And it applies to umbrella sampling, metadynamics. There are lots of acronyms, lots of methods, adaptive bias force, even Markov state model, free energy perturbation, replica exchange with solute tempering. There's this idea. You need to have your coordinates to do something. So for metadynamics, at least, this procedure is guaranteed to converge to the true free energy in the limit of long time. Greg Voth has a very nice proof on it in PRL where he shows how this can be mapped into a stochastic differential equation which has a unique fixed point. But the proof does not answer how much time will it take to converge to that unique fixed point, right? So if you have a good reaction coordinate, it will converge faster. And before I go into how we go on our search for a reaction coordinate, I want to show you that this can all be very useful. So my lab received some funding from Schrödinger, and one of the things we did in collaboration with them, this was actually when I was still a postdoc with Bruce Byrne, was they have this docking method, and I really don't know how the docking thing works. I know it's quite bad many times. What it does is to generate, you have a protein target and you have a ligand, and you want to generate what will be the bound structure. So docking will give you some 20 candidates or 50 candidates, and maybe in those top 50 there is one structure which is actually good. But that's still quite a lot, right? So they wanted a method which could quickly screen through these docking structures and rank all the bad ones. Say that, okay, these 45 are really bad, so don't focus on them. So what we did was to come up with a simple reaction coordinate which was kind of transferable, and show that if we applied metadynamics along this reaction coordinate on top of docking solutions, we could very easily rank structures. In fact, this method was used in an independent competition called Drug Design Data Resource Challenge, DDR2, by Eli Lilly, with no collaboration with Schrödinger, and they found that out of all the methods that they considered, this combination of docking and metadynamics came in number 4, but it's actually number 1 because the first method did not work on half the structures, and the other two, second and third, had expert pre-knowledge. So this was the only method that worked automatically on a very large number of structures. So we can do very useful things with such a thing, but we have a big chicken versus egg problem at the heart of sampling. So in other words, in order to know the answer, you need to know the answer. There is no other way, which means that in order to perform this sampling, go back and forth, you need to have a sense of a good reaction coordinate. How do you know a good reaction coordinate if you have not sampled the landscape, right? You have no idea what's going on. So this has been an open problem in the field, and I think we need sampling methods that can automatically learn the reaction coordinate as they learn the landscape. And I'm definitely not the first one to address this. Cecilia and Yannis both have wonderful papers which have inspired the remaining part of this research. Methods such as diffusion map directed molecular dynamics, or what Yannis did with Gerhardt, methods like this. But in the end, it becomes a question of how can you keep it as practical, right? It's always a question of, is it really implementable in a very robust manner? So let's see. So I want to introduce a framework before I go into the method. So the way we are going to find the reaction coordinate, and I'm going to focus mostly on drug dissociation for now. So this is benzamidine dissociating from trypsin. So I could have tried to find the reaction coordinate as a function of all 3n coordinates in this system, right? But I'm going to do a bit of cheating. I'm going to work in the space of order parameters, which could be contacts between the drug and the protein. It could be conformation of the drug. It could be pocket waters inside the binding pocket. It could be reorganization of the pocket. So so I'm taking the 3n dimensional space and already reducing it to something like 30, 40, 50 dimensional. So for instance, typically what we do in the lab is to look at all heavy atom contacts between the ligand and the protein. So if the ligand has maybe 5 heavy atoms and the protein has 300 heavy atoms, you're looking at a 1500 dimensional space, right? So we are not going from 100,000 to 1 or 2, we are going from 1500 to 1 or 2. If I have time in the end, I will show you a method how we do some pre-screening on this 1500 to bring it even lower. But yeah, but this is something to keep in mind. So we are working in the space of order parameters or features. Now, we have a paper currently under review where I'm having a bad fight with the referee who does not like the word order parameter being used for this, which is another story. But this is what I mean by order parameter. And then we want to build a linear or nonlinear model. So we really like linear models because the theme of this workshop, interpretability, it falls out naturally. We want to avoid nonlinear models as much as we can. And I will show you what we do there. So in order to do this, so we are going to focus on this part over here. And yeah, so if time remains, I will show you how we deal with this part towards the end with a method called amino. So before we go ahead, there is a warning. This warning reads as follows. Statistical mechanics does not tell us what the relevant variables are. This is our choice. If we choose well, the results may be useful. If we choose badly, the results, while still formally correct, will probably be useless. So anyone can guess where is this quote from?
Zwanzig.
He's been there, he's heard it. Yes, it is from Zwanzig. He has a wonderful book on non-equilibrium statistical mechanics, and it's in chapter 8 called Projection Operators. And this is Zwanzig. This is actually his office in University of Maryland. This is where I do my group meetings now. It was a very, very big office. So Zwanzig says, don't even try. You're not going to succeed. So let's see if we can prove Zwanzig slightly wrong by taking help from E.T. Jaynes and Bill Bialek also. I'm not going to get a hairstyle like that, but maybe there is hope for this. So one of the things about a reaction coordinate is you can define it exactly, and I didn't have time to draw it, but let's say you have a two-state system with potential energy wells that look like this. So if you go to this point and launch lots of trajectories from here, you will have a 50% probability of landing here, 50% probability of landing here, right? Let's go on a search for all points which have such a property of this 50-50% split. And let's find all those points. Let's find other points which have a 40% split probability, 30% split probability, right? So let's find these points, and then let's draw a normal through that surface. This is the perfect reaction coordinate. It's called an isocommuter. This is not useful, though, in my opinion. If Van den Eyden was here, he would disagree with me because they have methods trying to approximate the reaction isocommuter, but this is, I think, the perfect reaction coordinate. It does everything. But as you can imagine, if you had a brute force way of sampling this surface, you would have to go to so many parts in phase space and launch so many trajectories. It's not going to be practical. So while this is the perfect reaction coordinate, it becomes a bit impractical to calculate it. So we try to come up with working definitions of the reaction coordinate, which are approximations, and that leads to richness in the field. We can define approximations to this in many different ways, and each such approximation allows us to come up with a different method, which makes for a lot of fun. So the first method that I won't spend a lot of time on was something I came up when I was a postdoc with Bruce Byrne, which was inspired by methods like TICA and everything else, or Markov-Stern models in general, is that a reaction coordinate is a low-dimensional projection where the slow degrees of freedom and the fast degrees of freedom have the largest separation in eigenvalues. And you can show why this is a good projection. And the method which quantifies this that we published is called SCOOP, Spectral Gap Optimization of Order Parameters, and it uses something called maximum caliber. So when we came up with SCOOP, a month later, Vijay Pandey and Sultan came up with a method TICA-meta, while my other previous postdoc advisor, Parinello, came up with a method meta-TICA. They are in the same family as SCOOP, the idea being that you do metadynamics, do TICA on it, come back and do metadynamics, do more TICA on it, and iterate. There are theoretical questions here because TICA needs its time-independent component analysis, right? As soon as you do metadynamics, the notion of time is a bit distorted. So there are approximations there. But these are all, they are good methods in a similar spirit. So this is a schematic I took out of Kendall's paper. I think it's coming out in ARPC. And idea being that if you have a two-state system, you see that green is a better reaction coordinate, red is a poor reaction coordinate, right? So if you look at the statistics along green, it will look something like this. You will have very little population in the middle. You will have lots of population on the other side. So if you look at the ratio of the populations, you will have a clear gap. In this case, along red, if you projected the population, you will not get such a clear gap. Essentially, this we crudely call spectral gap. To find such a spectral gap, so remember, we are interested in rare event systems where we cannot just launch trajectories and actually collect the statistics. We are interested in systems where if we ran MD, we would just be sitting in the bottom of the basin and nothing would happen. So for this, we have to use this notion of caliber. So actually, I saw this name in the last talk also. So maximum caliber is an interesting concept that E.T. Janes wrote about in his paper in ARPC in 1980. It was revitalized by Kendall and Gerhard Stock and others in the last few years. The idea is as follows. If I give you the probability distribution along some trial reaction coordinate or some projection, let's say the probability distribution is probability A in this bin and probability B in this bin, what can you infer about the rate of moving between these bins? If you have a well-behaved physical system, the first thing you can write down is that KAB multiplied by PA is equal to KBA multiplied by PB, right? That's just detailed balance. But the thing is, this under-constrains the rates. There are many forms of rate which can still follow detailed balance. What MaxCal does is it writes down an expression that looks like maximum entropy, only now you have rates, so it's maximum path entropy, subject to what you know about the system. And if you maximize it, you get a very interesting square root expression. So this square root expression shows up naturally in MaxCal. One of the first places I have seen it is in the appendix of a paper by Attila Szabo in 1998, where he derives this by mapping a master equation to a Smolakowski equation. Gerhard Hummer popularized this equation in the context of getting diffusivity constants. And interestingly, in this paper by Yasha, I don't know, Sol Dickenstein. What is it? Yasha. In machine learning, he also uses this same equation in something called probability flows. And he kind of used it in an ad hoc manner. He said detailed balance under constrains it, so I'm just going to use a square root relation. But it actually falls out of some other physics, that why it has to be square root. It cannot be cube root, for example, or something else. But this is quite powerful because if we know something about the stationary probability, we can supplement it with some dynamical information about the system and quickly construct approximate kinetic models. So the algorithm then works as follows. We do our metadynamics along some trial coordinate. From this, we reweight using this particular algorithm to get the projection along any other coordinate. We run short bursts of molecular dynamics to get our dynamical observables. We build a crude kinetic model. We get the spectral gap from this kinetic model, and we pick the reaction coordinate which has the highest spectral gap. And we iterate this until the whole thing converges. This is one way this used the notion of reaction coordinate being something with a high maximum spectral gap. But the main focus of this talk is looking at reaction coordinate as something called a past-future information bottleneck. So that last work was something I did as a postdoc. This is purely made in Maryland work, mostly done by my first graduate student, Yang, who is sitting over there. I mean, I cannot salute him enough for his bravery for joining my group as the first student. But I think we have been having a lot of fun. So, and this method has a simple name. It's called RAVE, Re-Weighted Auto-Encoded Variational Base for Enhanced Sampling. The first paper came out in 2018, and this summer we published Nature Communication, which that's the form I'm going to show here. So this was the Nature Communication paper. So this notion of an information bottleneck was popularized by Bill Bialek, but it really goes back to Shannon and distortion theory, in my view. So the idea is that you have a high-dimensional input, and you want to come up with a model that tells you something about an output. Now, the output could be the input itself. The output could be some other high-dimensional output. It could be labels, some generic quantity. What we do here is to take the input as the state of a system at time t, and the output as the state of the system at time t plus delta t later. We are interested in stationary systems, so you can forget about t and just look at delta t. So what Bialek says is that a good model should have two properties. Oh yeah, before I go into what he says, I want to show you why we have this delta t notion. So imagine you are a frog trying to catch a fly, right? If you just focus on where the fly is right now, you will be a very hungry frog, right? You will never catch a fly. You have to think about where the fly is going to be a few time steps into the future. Similarly, if you're playing baseball, or when I was young, I wanted to be a cricket star, growing up in India, and I was horrible at it because I would never focus on where the ball is going next. And that's the trick, right? But you also can't focus on how far into the future, not a few time steps into the future. Few time steps is okay. If you focus too far into the future, then also you're going to be a bad cricket player or a hungry frog, right? So it helps to be able to figure out that you have to look a little bit into the future, but not too far. So we want to take these models that Bialek has proposed for example, how a fly goes around looking at things, or how the retina processes something else, and apply it to how a ligand dissociates from a protein. And to quantify it, what Bialek says is a good model should have two properties. It should compress the input as much as possible while still being as predictive of the output as possible. So the mutual information between x and this bottleneck variable chi should be as low as possible, while the mutual information between the bottleneck and the output should be as high as possible. So you can write down an objective function which looks like the difference of two mutual informations. It has a Lagrange multiplier over here. If you set this is equal to 0, then you are simply not caring about the compression part. You are only interested in prediction. If you make it too high, then you are not interested in prediction. You just want to capture everything about the input. And if you set beta is equal to 1 and try to predict the input itself, you recover a variational autoencoder. So in a certain way, it's a generalization of a variational autoencoder. And the paper that really started us on it was this paper by folks at Google called Deep Variational Information Bottleneck, where they talk about all of this as to why is this a generalization of variational autoencoder. So how do we do this? This is where statistical physics again starts to play a role. You could write down an encoder, right, which gives you the probability of the bottleneck knowing the input dimension. So when poor Jehan started with me, I said, well, now you can use Bayes' theorem and write down the decoder exactly. So Jehan went full of energy, and he comes back to me, well, this thing is exploding in dimensions, right? Because Bayes' theorem, if your input is 3-dimensional, Bayes' theorem involves six-dimensional integrals. So due to the denominator, it really explodes. So variational inference goes back to Feynman, and depending on the citizenship of the author of the book, you can see any combination of these names. I have seen at least one place all 5 at the same time. So what it says is, instead of working with the exact decoder, which you could write down in principle just by Bayes' theorem, work with an approximate decoder. Once you work with an approximate decoder, your bottleneck function gets supplemented by a KL divergence. So, and KL divergence is a nice metric because it's strictly non-zero, right? So what it means is, instead of, so let's say this jagged line over here is the exact decoder that is hard to calculate. We come up with some approximate decoder, and we maximize this objective function on this approximate decoder, go back, improve the decoder itself, come back and maximize it until both the processes converge. So it's a double optimization process, and we don't have to deal with very high dimensional integrals. And remember what I said earlier, so we want to keep the model linear for now, unless we are completely just, before we delve into nonlinearity, we want to see how far we can push a linear model. So in order to do all of this, the way we implement it is that we use a linear encoder. Even with a linear encoder, this decoder becomes extremely complicated. But in order to capture the complicated features of the decoder, a deep neural network is ideally suited because it has that sort of expressibility.
Since the
Yeah.
encoder is already nonlinear, what does it help if the encoder is linear?
Because decoder is just for bookkeeping in the head. We don't need it. The decoder is used only in the training, right? When I give it to someone to use as a reaction coordinate, they don't care how the decoder came.
Okay, so at the end, you would like to have a linear encoder for ease.
Yeah, ease and debugging is a huge part. So our network looks like this. It's got an encoder, it's got a deep neural network, and it allows us to predict the evolution of the system. This is not all 3 in coordinates, this is order parameters, delta t into the future. Now, sometimes a one-dimensional linear encoder is not sufficient, whereby sometimes I mean almost every time. So what do? We don't add depth here, but we try to learn a second component of the latent variable, but also keep that as linear. So in other words, instead of making this more nonlinear, we are trying to come up with more components which are kept linear. It's not other words, the same thing I said again. So that's what we are trying to do, but for now, this captures the picture, what we have. So, okay, all done then, right? We are wonderful, everything will work, but it's not as simple. Even with a linear encoder, we run into troubles, and I'll show you how. So this is a website at Stanford where you upload a picture, and from the picture, it generates a text. So when it works well, it works beautifully. You know, man in black shirt is playing guitar, girl in pink dress is jumping in air. Oftentimes it doesn't work, and then it looks something like this. So this is due to my earlier postdoc, Joao Ribeiro, who is now a senior postdoc in Mount Sinai with Marta Filizola. So he found these images where surfboards on a beach, right? Bunch of bananas are on the table. Cat looking at pigeon? No. Group of people standing around a horse. Bird on a beach? No. Small airplane flying in the sky. So this is quite important because you threw a molecular dynamics trajectory into the deep learning module, and instead of telling you that you should enhance fluctuations in the space of surfboards, it tells you to go enhance fluctuation in the space of bananas. And it's possible that good surfers are also eat lots of bananas. So in the limit of long time, you might get the right answer, but it will be for the wrong reason. How bad is this problem? Do we see it in molecular dynamics? Well, we do. This is an example. So this summer, I got a student from Emad Tajorkish's lab at UIUC who visited us for the summer, Shashank Pant, and he did this work, so it's thanks to him, where he took alanine dipeptide, the hydrogen atom of these simulations. I think we saw it earlier in Cecilia's talk on first day. So this is alanine dipeptide. As you can see, it's a rare event system, right? This system stays most of its time in this basin, goes to the other basin only once or twice. You take this trajectory, and you train different rounds of rave on it. By now, I have not shown you the full rave. I have just shown you the neural network architecture. But the same trajectory with slightly different seed, you stop trials at the same loss function. And it's a linear encoder, right? So we can directly read off the weight of the different order parameters. We can see what we got. So the question is, for the same loss function, which looks like it's very well converged if you go and see at the plot, how different are the reaction coordinates? The answer is very, very different. You cannot just look at the loss function and say, we have done the job. It could take you to somewhere completely different. Now this is a simple problem. You can go and construct the free energies of these 7 reaction coordinates, and you will be able to tell that actually 6 of them, or 5 of them are very bad, and 1 or 2 of them are good. Please.
Isn't that a failure of your loss function? If you have 6 solutions to your loss function and 5 of them are bad, doesn't that mean you've not correctly encoded your problem?
Absolutely. But what do I do then?
Are they bad or are they equal?
They are not equally good. 5 of them are quite bad. So you are right. Perhaps we could go in that search. You're right. But this is a typical loss function which has a linear encoder. And same thing, if I make it more complicated, if I start using a deep encoder as well, this problem only gets worse. That the loss function does not.
Anytime your loss function is not what you actually care about, you're in trouble.
Yeah, and the reason this happens in MD more often than other fields is because you think of MD and you think, I have all this data, right, and I can go and fit a neural network. But most of the data is not good. It's just trapped in one state. So I think I have heard mathematicians talk about in the limit of infinite training data and in the limit of infinitely expressive deep networks, everything is convex. But this is just one data point really. So that's the reason it happens. So in fact, I should have shown you the slide where if we increase the length of this trajectory, this problem tends to go down. The loss function starts to do better, which is good, but this is alanine dipeptide. Forget about curing cancer with this. So we have at least 2 problems if you just want to use deep learning on molecular dynamics trajectories. One is that we want to learn interpretable solutions. Well, I came up with a poor man's solution. Just keep the encoder linear, right? You can directly read off what's going on. And the second is it has its own sampling issues. And that goes back to the first introductory slide that I showed you where I asked the question, is it Goodfellow or Tuckerman? So for this, I will show you one solution next, but the other solution that we are working on, and we don't have a manuscript yet or anything, which is to take these different solutions and build a crude kinetic model, to build a max scale model on top of deep learning solutions. And we can cleanly see that most of them don't have a spectral gap. They are just crab solutions. And this way also we can rule out. So this is actually complementing the loss function. Instead of just having a training type loss, we are building dynamics into the loss function. But this one, let's see what it does. So here you have alanine dipeptide, which is trapped in, so this is the full algorithm now. You have alanine dipeptide, which is trapped in one basin. You take this trajectory, you try to learn this predictive information bottleneck. Here I am showing you the bottleneck as a function of 4 order parameters. You have torsions. So we are learning a linear combination. You cannot just take a linear combination of angles, right? You have to take combination of the cos and sine of the angle. So that's why it has 4 parameters. For this trajectory, depending on how far into the future you're trying to predict, the reaction coordinate kind of does not change. If you use some regularizer, all of these would go to 0. So you just get high weight for 1. What we can do now is to take this coordinate, this particular definition of the coordinate, say when it has converged, and its probability distribution, and use it as a bias for the next round of MD. So this was the probability distribution. So the autoencoder, the way we are using it, or in general, is not just learning a latent variable, it's also learning the probability distribution of the latent variable. And that's something we are trying to exploit here. So we have this probability distribution. We can invert it to use as a bias for the next round of simulation. And this is one way we can rule out spurious minima. So if we got 4 different solutions, we will get 4 different biases. We will do 4 different MDs in the next round. 3 of them will just get trapped, will not improve. The good solution will actually enhance ergodicity. It will make the simulation more ergodic. Now that leads to even more theoretical questions. How do you know that it has become more ergodic or not? But most of these problems, we have a sense of a progress parameter. So we can see whether the progress parameter improved or not. So we take our best solution, what we think is likely the surfboard and not the banana, and do a next round of biased MD, feed this biased trajectory to the neural network and learn. So when we feed a biased trajectory, you have to keep in mind the data points have to be reweighted because they are biased. So you have to account for the fact that it's not a Boltzmann trajectory. And then you go back to MD, and in the second iteration of MD, you see that it automatically escapes into the other basin and comes back. And at this point, you can do one more round, but essentially this reaction coordinate converges. If you do more rounds of machine learning and MD, the reaction coordinate does not change, and at this point, you stop the algorithm. That's simply rave. It's quite nice. We iterate between CPUs and GPUs. Yeah, Andrew.
So wouldn't this be really susceptible to the length of your iteration trajectories? You could
Absolutely.
basin and just move back and forth?
Absolutely. So longer the better. If you can run your MD really long, the better it is. We try to push it with something where it's a fight against the queue time on Exceed, right? It can start quickly and we can get our MD running, so a couple of hours, which is maybe a few nanoseconds. But I think it's better to do it for very long time series. And it's as simple as that. Longer your time series, the better it is. In fact, if you have seen the rare event, you can also start iterating between rounds of metadynamics, right? Instead of doing unbiased MD, you do metadynamics between 2 rounds. And that's the practical approach we are taking now. Then it's super fast. So yeah.
So in your reweighting, it's thermodynamic reweighting.
Yeah.
But you have a sort of a temporal principle underlying.
Very good point. So where's Yehang? On his poster, he agrees about that. So what, yeah, you're absolutely correct. In the first paper, we kind of ignored the fact that there is a static thermodynamic reweighting and the propagator also has to be reweighted. And we actually came up with a correction for reweighting of the propagator. And we found that in the short delta time limit, it does not make, the correction makes some difference, but not a lot of difference. But we have a correction for that also. That's an interesting problem. So go see his poster. We'll send you the preprint when we have it. So yeah, and we can systematically increase the dimensionality of this reaction coordinate. We can learn other components, still keeping them linear. So let's go to some applications. So we had some, so I had one team of rotation students essentially at that point look at this problem of how does benzene dissociate from lysozyme. So lysozyme is a small protein. Nothing really binds inside it, but a few decades ago, some biochemists realized that if they mutate one residue to alanine, it opens up a hydrophobic pocket. And this hydrophobic pocket is so hydrophobic that suddenly everything binds inside it. Benzene, neon, krypton, argon, xenon, radon, all the things due to their mutual distaste for water like to go inside and sit there. And it's a very well-studied system where we took 11 order parameters in this case, so lots of protein ligand distances, some protein-protein distances, and we asked if two different methods, scoop followed by metadynamics and rave, give the same pathways or not, and same kinetics or not. So, and here, especially when you do kinetics with molecular dynamics, it's very sensitive to the force field you use and a variety of things. So here or even how you parameterize the ligand. I mean, kinetics is really a log scale game. Any agreement within order of magnitude is good agreement. So we got the force field and everything from Kresten, Lindorf, Larsen in Copenhagen, who was actually one of the co-authors on that monumental D-Shaw paper back in the day. And this is the trajectory that we get. In order for this to dissociate, the ligand has to move between alpha helices. And it could have gone through these two alpha helices, these two alpha helices, these two, or these two. It always goes through this one. So just to give you a bit of perspective, this trajectory is coming from the final converged bias that we got out of rave. So we ran maybe 10 or 20 rounds of rave where we iterated between MD, machine learning, reaction coordinate converged. We got a final static bias. And now we can do MD with the static bias without any more machine learning, where the ligand just goes back and forth between all points and escapes on its own. And we look at the kinetics, and it's very similar to what Kresten obtained and also what we got with our other methods. Now that we have the reaction coordinate, we can make more predictions. We can look at the mutual information between the reaction coordinate or the information bottleneck and different parts of the protein and see which of them have high mutual information. So most of them are in the binding pocket. Some of them lie out here. So when we published this paper, the referee was absolutely correct. And the referee told us, well, this might be fortuitous. You have to go back and do it with different choice of input order parameters. So we did that. The result was that we did not get exactly the same residues, but we got very similar residues in that part of the protein, even with different order parameters. So this goes back to the picture that I showed you early on regarding predicting which mutations in the protein could have an impact on the process. So now we are doing some in silico experiments where we are mutating the protein here and seeing if it actually affects the process or not. So it persists with other order parameters. So why do we have to try to predict slightly into the future? For alanine peptide, it does not make much of a difference. For benzene lysozyme, it makes a huge difference. However, I must point out, this was before I attended Andy's talk and Brooke, where is Brooke? Brooke's talk in Paris, where they introduced me to the notion of whitening, which is to essentially make the data variance free. We were not whitening. What we find now is that many systems, if we whiten the data, the time dependence seems to decrease. Not always, but many times. So that's technical, but I think it's interesting. So, but you can have situations where if you try to predict slightly into the future, the thing converges very easily, so you don't care about what exact value you take, because each of these is a lot of MD and ML solutions mixed together. So you can just take something which is around 2-3 picosecond and just stick with it. And we can now interpret it. The way we can interpret it, so our order parameters, 8 of them were protein-ligand order parameters, distance between protein and the ligand, and 3 of them were protein-protein order parameters. So the interesting thing is that Scoop and Rave both give different order parameters. The exact order parameters are not the same, but they both capture this physics. If you look at the green one, there is a protein-ligand order parameter that has a positive sign, and there is a protein-protein order parameter that has a negative sign. So what it is telling us is that as this thing goes closer to this distance, the protein-protein has to squeeze out, and it is capturing that physics. And for enhanced sampling, that goes back to that picture. You don't need to have the perfect reaction coordinate. As long as you have some overlap with the reaction coordinate, it gets the job done. And that's what we are seeing here. And then we apply it to more complicated systems. Well, this is not RAVE, this is SCOOP on the actual anti-cancer drug that I showed you earlier. And now we can go and see what really goes on, which parts of the protein have to distort for the ligand to leave, and we can make predictions. So this is in collaboration with Markus Seliger at Stony Brook, who is now actually synthesizing these protein variants based on our predictions and seeing whether they're correct or not. So, and yeah, there are more applications. This is a paper I started writing with Bruce when I was a postdoc. It's still not written. I have to finish it at some point. But in how much time do I have? 4 minutes. Oh, perfect. Very good. So I'm going to show you something which is just on bioRxiv. It's work done by undergrad in my lab named Pawan Ravindra. This is a rising junior. So he was a second-year undergrad. When he started, he was a triple major in computer science, math, and biochemistry. Now he's a double major. And he's also world number 6 in solving Rubik's Cube with one hand. So it's an interesting guy who will be applying to grad school. So he's very interested in these things. So I gave him this problem of how to come up with order parameters. Yeah, undergrad, best problem for undergrads, right? So essentially, all these methods like SCOOP or RAVE, in principle, they can work on any dimensional input space, right? Even TICA can work on as big as your input dimensional spaces, right? You can consider all heavy atom contacts between the protein and the ligand, but it helps if you can reduce that space. And why do you want to reduce that space? Because most of the contacts are just correlated. They are not capturing more physics. So if you could have an automatic procedure for taking a lot of order parameters and reducing them to a minimal set of order parameters, then it will help our actual reaction coordinate method. That's the idea here. So this method is called AMINO, Automatic Mutual Information Noise Omission. And the idea is that let's define a new distance metric between different order parameters on the basis of what information they carry. So if two order parameters have the same number of basins and things like that, they will be classified as similar order parameters. If order parameters are all looking like noise, they will fall into some other basin. So maybe these are all noisy order parameters. These are order parameters with one basin. These are order parameters with two basins. That's the rough idea. So then you use this mutual information based distance metric to cluster all these order parameters. So if they have less mutual information, if they have a lot of mutual information with respect to each other, actually the term we actually use is called information quality ratio, which is 1 minus mutual information. We should have mentioned that here. So, and then we cluster it, and then we pick the most representative point from each cluster. What it does not tell us at this point is how many clusters do we need. For that, Pawan found out a very nice work by Sugar and James in American Statistical Association 2003, which uses rate distortion theory, which is interestingly the preceding form of information bottleneck. And it allows us to actually quantify by looking at something called distortion jump and say, how many clusters do we need? So it looks noisy, but you can, for complex systems also, we can figure out what is the peak. So this plot here is showing us for different hyperparameters, we always get a peak at 8 order parameters, and we can see which are those 8 order parameters. So for this system, which is a small ligand BUT dissociating from the protein FKBP, if you look at all protein ligand heavy contacts, you have 428 contacts. When you apply amino on it, you discover these 8 contacts to be important, which are shown over here. You apply SCOOP to it, you get a reaction coordinate comprised of these 8 contacts, and then you can do metadynamics on these. So for this system, Albert Pan performed simulations on Anton, on D. Shaw's computer, where you can see the black line is the unbiased estimate coming from Anton, which took a lot of computer time in order to converge it. It was run much longer than 10 microseconds or something. This is with metadynamics along this coordinate, and it converges within error bars very quickly. This is our attempt to do unbiased MD, which would converge almost logarithmically, or yeah, extremely slowly. So this is quite nice because the code that we have now just takes a PDB structure, generates all heavy contacts, reduces them to a minimal space, performs scoop on it, goes and launches Metadynamics, and you end up with a converged free energy. So we're really trying to automate the full thing. It was possible in principle, but these little things make a huge difference, and that's what we are doing here now. And these are also some other reaction coordinates from Metadynamics. What if we picked intuitive reaction coordinates, and we find that the scoop amino reaction coordinate actually beats all of them? So with that, I think I can summarize now. I introduce a so-called learning to learn perspective, which means it goes back to importance sampling. Importance sampling is wonderful, but you need to know the importance function, right? You can come up with a zero variance estimator in importance sampling if you knew what is the answer. If you don't know the answer, so you have to learn it on the fly. I quickly went through 3 different methods: scoop, rave, and amino, which are enhanced sampling methods that allow you to get to very long time scales. And the way we are envisioning everything is to directly go from PDB and get a final mechanism or kinetics or free energy. And I showed you case studies in ligand protein and binding. I did not talk about our work on how ligands dissociate from RNA, and also not about crystal nucleation. The scoop and amino codes are out on GitHub. And rave code, we have been emailing to people who have asked us for it. We are still fine-tuning a few things, but a public release should be out soon. And most of these use Plumed, which is started as a plugin for Metadynamics, but it allows you to do all sorts of enhanced sampling. And I think mostly they use Keras and TensorFlow. We are not using PyTorch, at least as of now. Yeah, with that, thank you very much. And I wanted to say that I guess when I made this, I did find PhD students, but I'm still looking for a good postdoc. When they write to me, I ask them to code something basic, and for whatever reason, most of them run away. So if you have good coders, please send them to me. Thank you very much.